So we're going to start with the next topic, which is reaction kinetics. Okay. So remember you did some reaction kinetics in AS and O levels, but that was very, very basic. So this is what you studied in reaction kinetics. The first thing is, I mean, you can call it rate of reaction. Now, the very first thing is that when you talk about the rate of reaction, so we've got many different types of reactions. We need to first understand what is meant by the term rate. So when you see a reaction that's happening quickly or slowly, what exactly is rate? Rate is basically proportional to any change that happens with respect to time. Okay, so any change which happens with respect to time. So it's inversely proportional to time. And this change that we're talking about, this change could be any change. Whenever you have a reaction going on, many things could change. So it could be the change of color, or the mass could be changing, or the concentration could be changing, or pressure could be changing. So it's any change. If that change happens very quickly, for example, if the color changes very, very quickly, that means the reaction is happening very, very quickly. So when you want to figure out whether the reaction is fast or slow, you're going to just measure any change as long as you're consistent. For example, if you're measuring the change in mass, then in all experiments, just for fair comparison, it's important that you keep the variables constant. So I've got a reaction in which I've got Mg reacting with HCl, and it's forming MgCl2 plus H2 gas. Okay, this one is solid, this is aqueous. अब मुझे बताओ कि if you look at this reaction, what are the different ways in which you could measure the rate of the reaction, whether it's happening quickly or fast? So what are the changes that you could measure? And remember, the change has to be observable and quantifiable. अच्छा, इस reaction का कोई बता दे कि Salih, Tasneem, any idea what will happen if you want to measure the rate of this reaction? What change should you measure?
How fast the magnesium solid dissolves?
Okay, so you can check how quickly, or what you can do is you can measure the mass of Mg, the remaining. With respect to time. So other things that you can do is you can measure the volume of gas. And again, with respect to time. You can measure the change in concentration of HCl. And again, with respect to time. So you can measure many different things when you're trying to measure this. So you'll plot them on a graph paper. One of the axes is obviously going to be time. And the other axis is going to be your change. which is going to be plotted. Now that change could be an increasing change or it could be decreasing change. For example, if you're talking about the volume of gas, then the volume of gas would increase. And then at a certain point, it will become constant. So initially there is no H2 gas, but then slowly H2 gas gets formed. Okay, so slowly H2 gas is going to get formed. As a next, if you're measuring the mass of Mg, then initially you're going to have a lot of mass. And then the mass will start to decrease. So you could have an increasing change, or you could have a decreasing change, and you can plot it against time. The gradient of this graph of the change plotted versus time, that's going to be your rate of reaction. So gradient of graph is equal to rate. If the gradient is very, very steep, that means the reaction is fast. If the gradient is less steep, that means the reaction is very slow. And if the gradient is horizontal or zero, so that obviously means that the reaction has stopped. So in this case, the reaction has completely stopped. If there is no now remember, gradients can be increasing or they could be decreasing. So that's, and the gradient keeps changing. So that means a rate is not something that's constant. It's rate itself is a variable. But what it does is it varies with respect to time. Usually, normally, any reaction is fast in the beginning, and then they tend to slow down. But remember, that's not always 100% true. I mean, there can be exceptions. So the thing is that if you're trying to measure rate, it's always better to measure the initial rate. The first tangent that I've drawn, that's my initial rate because that's the tangent of the graph at time t is equal to 0. So right at the beginning, so we're more interested in initial rates. So always measure because it's kind of pointless to compare two experiments after 10 minutes when the reaction has sufficiently slowed down. So there's no point comparing two reactions after 10 minutes or 20 minutes. It's always important to measure initial rates, which is t is equal to 0. for comparison. Okay, is this part clear that you always measure initial rates?
Yes, sir.
Clear?
Yes, sir.
Achha, so you always try to measure initial rates. Now, so always remember that when you're doing comparison, it's always to measure right at the beginning, not, I mean, they can ask you to measure the rate of the reaction at, let's say, 10 seconds or 5 seconds, but at 0 seconds, that's important. I said, then also remember that one thing about gradients is that ignore the sign of the gradient. Because that only shows that the change is increasing or decreasing. When in fact, we're not really interested in whether the change is increasing or decreasing. We are mostly interested in the fact how steep is the gradient. So we're actually more interested in the steepness, not in the direction. Whether it's a rising gradient or whether it's a decreasing gradient, that is not our concern. ठीक है? Is this clear? Is this thing clear?
Yes, sir.
Yes, sir.
Achha, another way to measure rate where you don't have to plot a graph. Achha, so comparing rates. Comparing rates without graphs. Now, when you want to do this, what you're going to do is, I told you that rate is basically change with respect to time. Now, one thing about the graph method of measuring a rate is that it's too time consuming. You have to plot a number of points. You have to take a number of readings. For example, if you're measuring the volume of H2 gas, you'll measure the volume of H2 gas at regular time intervals and then plot a graph. And then you're going to take a tangent and then you're going to find the rate or the speed at which the volume of H2 gas is getting produced. So that kind of takes a very, very long time. So an easier method is you don't make graphs and you can just take one value, which is what you basically need to do is you need to fix this. So let me explain. Like you've got a 100-meter race, and let's say they're like 4 runners sprinting a 100-meter race. Now what you're not going to do is you're not going to plot every 5 seconds or every 1 second how far the runner has traveled at a particular time interval, then make a curve, and then you're going to try and plot the speed of the runner, right? Because that's going to be too time consuming. So instead, what they do in a 100-meter race is they never actually calculate the speed of the runner. What they instead do is they just measure time. The only thing that's measured is time. And you're just going to keep change fixed. So for example, you're going to try, like if you have an Mg and HCl reaction and you're doing it at different temperatures, or you're trying to figure out the rate of the reaction under different concentrations or under different other different changes you're doing to the reaction. So what you're going to do is you're going to keep the change fixed. So for example, you're going to measure time needed for 15 cm cube of phase 2 gas to form. So you're going to fix the change. Okay? So you're not going to measure the change at regular time intervals. Instead, you're just going to measure one change. And every reaction, like if there are 10 people doing the same experiment, each one of those 10 people will measure how quickly 15 cm cube of H2 gas gets produced. And what they'll do is that will give them different time values. So since your change is fixed, your rate then becomes inversely proportional to time. That is exactly what you do in a 100-meter sprint. You just measure time. The lesser the time, the faster the reaction, or faster the runner, right? So is this part clear that you can measure the rate of a reaction without making any graphs or tangents? Is that clear?
Yes, sir. Yes, sir.
Saru, clear?
Yes.
Achha, so broadly speaking, there are two methods and of measuring rate. Now the next, but remember the key points. If you're doing this method, you're plotting, ignore the sign of the tangent. It doesn't really matter whether it's downward or upwards. Steepness is what rate of reaction is. And always try to compare initial rates, not the rates after a certain time interval. Without graphs, rate is just basically inversely proportional to time. The condition is that the change is always fixed. You always try to measure the same change with respect to time. I said I'm just going to recap some O-level stuff, which is factors affecting rate of reaction. I said broadly speaking, there are 5 factors. So factor number 1 is temperature, which is higher temperature would mean more kinetic energy. And that would lead to more frequent and effective collisions. Second, factor number 2. It's pressure. But that's only true for gases. Now, when it comes to pressure, if you have a higher pressure, you got lesser volume. So that would mean less gas volume. And that would mean that the particles are closer together. Which is why you're going to get more frequent collisions. अच्छा फिर इसको खत्म कर लें. Number 3 is that as a concentration that's only for gases and solutions. Normally it's only for solutions. So the higher the concentration, that just means that particles are closer together or more crowded. And that would also lead to more frequent collisions. I said, or consider which other two factors are there?
Surface area, sir.
So number 4 is your surface area. Now, surface area is that if it's smaller pieces, that means powdered. So that would just mean more surface area. That would mean more frequent collisions. And so finally, number 5 is number 5 here.
Catalyst.
Number 5 is catalyst. So what do catalysts do? They decrease activation energy. And they provide an alternate path. An easier path for the reaction. And if activation energy decreases, you get more effective collisions. So keep this in mind that when it comes to, temperature, you get both things. You get more frequent collisions and you also get more effective collisions. The collisions are more in number as well as they're more violent because there's more kinetic energy. In pressure, you only get more frequent collisions. The same applies to your concentration. Your surface area, you also get more frequent collisions. And you get more effective collisions. So the number of collisions in a catalyst, they remain exactly the same, except that they're more effective. So out of 100 collisions, more collisions will be successful. Okay, so you've got this chart, and always remember how to explain things when it comes to these 5 factors. I said then there was a thing called the Boltzmann distribution in AS. Now the Boltzmann distribution was a distribution of molecular or atomic energies in a gas or maybe in a solution as well. So let's say you've got a gas or you've got a mixture of gases. It will have a number of particles. So for example, there's N2 and H2 reacting. But okay, forget the reaction, right? Let's say this is air. So we've got a number of particles. And the Boltzmann distribution looks like this, that it's going to be a curve that's going to be skewed to one side. This side is the number or proportion of particles. And this axis is your energies, your molecular energies. As so at low energy, the number of particles are fewer. Like if you have a room, then the number of particles at low energies are not, at very low energies, they're not going to be very high. At very high energy, the number of particles are still not going to be. I mean, there's still not going to be a lot. I mean, the height is the number of particles. Most of the particles would be at room temperature, for example. So at your average energy, this is not the average, by the way, this is the most probable energy. So you have maximum number of particles. And remember, average energy is something that's slightly further to the right. So most probable energy is the energy at which you have the maximum number of particles. Average energy is that you take all the particles and you average out the energy of the particles. So that is what average energy is, which is slightly further to the right of the peak. Okay, remember you've done this in ASE. Clear enough, Sarah Boltzmann distribution.
Yes, sir.
Yes,
So
sir.
tell me, where would the peak move if I increase temperature? This side will move. If I increase temperature, it's going to shift.
Is it to the right, sir?
It's going to shift to the right. So this is the same curve at a higher temperature. At high energy, the number of particles have increased. At low energy, the number of particles have decreased. Vice versa, if I decrease the temperature, then the curve would get skewed to the left. So at lower temperatures, you're going to have more particles at lower temperatures. At high temperatures, you're going to have fewer particles if you decrease temperature. ठीक है, ये दोनों चीजें clear है?
Yes.
Yes.
Okay, so let's continue tomorrow then. Because we didn't really do much. I'll talk about the catalyst over here as well. We didn't really do much, mostly revision. Okay, we did something about how to measure the rate of the reaction. The factors affecting rate and a little bit about Boltzmann distribution. Otherwise, you didn't do much in AS. Okay, so tomorrow we'll probably continue with the important things related to A2. ठीक है? इसमें तो कोई क्वेश्चन नहीं है, ठीक है? This is mostly revision. तो कल कंटिन्यू करते हैं, ठीक है?
Yes, sir. Thank you. Allah Hafiz.
चलें. Okay, take care. Allah Hafiz.